And that is the only time I'll ever tell you my actual age. All right. So as we're looking at these, today we get to start a new section, and we're going to be doing some stuff up on the board and around and such. But I have a challenge for you first, and I really, really liked the way that Miss Sweet approached this with the other class. So we're going to have a similar approach to start us off. So here we go. Today in 7.4, and I am recording, so I'm cool with that. We are going to be talking about similarity still, but we're going to be talking about similarity that happens in pretty nice triangles. Now, that is a subjective statement. If I said, what's a nice triangle? Vincent, can you tell me what you consider a nice triangle? An isosceles is a pretty nice triangle. Anybody have a different type of triangle that's nice? A right triangle. I think both of those are nice, and there are isosceles right triangles where it overlaps. We're going to be talking about similarity in right triangles. Similarity in right, and I'm going to use RT for right triangles. Okay, now, before we just kind of kick off into this, I'm going to sketch one large right triangle first, and this is kind of it's not really its own section, but if we want a section to name it, we can call this intuition. We're going to see if we can develop some intuition ourselves on the following piece. Now, today, you are going to be working problems together in your groups. I don't mind if we go up to the board today necessarily, or if you guys are working at your desks, as long as people turn them around. But remember, front seaters, you're going to be turning your desks back and forth periodically throughout the day. Okay, intuition, that's all we're after. I want you, for the following picture, I want you to add a single line to the following. So we're going to add a single line that creates 3 right triangles. I don't know why I wrote the word right, but here we go. I want you guys to add a single line to your triangle, and your triangles won't be exactly the same, but they're all going to be essentially the same. A single line to this wonderful triangle, and we're going to make it this one. So here's a lovely triangle, and we'll call it LOV. I want you to add a line somewhere on this triangle such that, sorry, I'm going to make one more specific thing. That's a right angle. We're going to add one more line onto this triangle such that instead of having one right triangle on the board, we get 3 total right triangles. I'm going to give you and your neighbors a little bit of time. I don't think it's going to take a crazy amount. But let's see, 60 to 120 seconds with your neighbors, and you guys can just turn your bodies or physically turn your desks. I'm cool with either. But can we add a line that makes 3 right triangles? You've came up with this ultimately. Now, the nicer your triangle looks, the easier this is. And where do you want me to put my pen if I'm going to draw this third line or segment? Where should I draw the third one? From L? No. Okay, so from V? All right. Oh! Why is this one the magic line? Do we see 3 triangles?
Yes.
There's a left triangle, a right triangle, and a big triangle. Now, because we are talking about these lovely right triangles, it is appropriate that we'll call this point E for the time being. And here's my additional follow-up. I now have 3 right triangles on the board. Are they all, they're all right triangular shaped? Would we agree with that? Do you think there's anything special about those triangles? So no would be the appropriate answer if that's the feedback. What have we been talking about, and where do you think this might be leading? Maybe, just maybe, we create similar triangles. Now, that seems like a reasonable thought, right? Like, this is what we've been talking about, and obviously we get this going. Do you think they're similar? Do they look similar? Maybe, maybe not. I don't know. That's different. They don't super look similar to me, but that's just because it's a drawing. Like, I didn't put a whole lot of energy into it, I don't think. Could we show that they're similar? So I guess is a fine answer. But even more than that, yes. And you're going to. Because I'm going to make a claim, but you shouldn't just believe a claim that Holloway makes, right? Like, I mean, if I'm saying something about math, most of the time you should believe me, but I misspeak sometimes. Here's my challenge. We're going to use the same thing, and I just want you to try to do the following. I think that it's reasonable to say that these three probably similar, just based on what we're talking about. But I want you to justify, which is my way of saying, write me a logic proof, not like formal proof, but justify that we have 3 right triangles. And I'm going to give you guys a couple of more minutes working with one another. My advice to you is the stuff that we talk in math keeps building and building and building on itself. We have some shortcuts that we will use and that we have used. There are 3 shortcuts. What are they? To show similar triangle. Excuse me. Angle, angle? SAS? And side, side, side. Do you know any side lengths right now? Okay, so maybe that will eliminate at least something. I want you to see if you can justify, are these 3 triangles similar? And justify that they are, or convince me they're not. And then after that, we'll come back together, we'll write statements and follow-up stuff. You get 2 minutes, 5 minutes to try to show me logically that. Okay, each of your 2 groups, you played around with these and we recognize something. Now, with one of your groups, I took the triangles, or helped you rather, take the triangles apart so we could look at all 3 of them. But I think we can make the same argument here. Can we all agree there's 3 triangles on the board? Yeah. Like there are. Now, we're going to give ourselves a theorem from this picture. So we need this theorem, and we're going to give ourselves right now theorem 7.4. And it does not get its own name. But we started with a big triangle, and specifically it was a big what? So we started with a big right triangle. And then beyond that, we added this green dash, or this green line, which is what everybody came up with. This large line, does it have a special name with regard to this triangle? It goes from this point and goes all the way to the bottom, and it's perpendicular. So I don't see anything being bisected, but there's another special thing. Do you guys ever remember talking about orthocenters or centroids or incenters and all that good stuff? The orthocenter is a weird one that doesn't really fit in with the others. And if I wanted to find the area of a triangle, is what I think of with orthocenter stuff, how do you find the area of a triangle?
Base times height divided by 1/2.
1/2 base times height. Now, height is a more common word. Have we ever used another word for the height of a triangle? Louder? The altitude. Can we all agree that for this is an altitude right now? Like the line that you guys drew, it went from the highest point, if the bottom is what we call the base, it went from the altitude to this other side. Sorry, from the highest point to the other side, perpendicularly. That makes it an altitude. Now, with regard to the big triangle only, I draw the altitude from the right angle, and then I go to the, what side of the big triangle is LV? Is it a leg? So you could call it a base, but what if we're thinking right triangle language specifically? A leg, or the... It's the hypotenuse, isn't it? And it happens to be the base on the way that we've drawn it. But as we're looking at this, we're going to put those pieces together. If, and we're going to change it to an if. We're going to say, I lied. If an altitude is drawn on a right triangle, from the right angle to the hypotenuse. I'm going to shorthand hypotenuse with hype. If an altitude is drawn on a right triangle from the right angle to the hypotenuse, which is that exactly what we have drawn here? Yeah, I think so. If this happens, then we have how many similar triangles? 3 similar triangles formed. Okay. That is what we just witnessed. And we know that they're all similar via which shortcut did we use? Angle, angle. Now, where I like to go with this, and it's different depending on the teacher, and the books all present them differently, is we can take an approach where we take these things apart and we start trying to get it to line up, which is totally valid. I struggle with it. Again, I don't know why. I have a really hard time personally thinking about these triangles spinning around. So I like to rely on the fact that we can write it down without having to being able to imagine all this spinning and stuff. I want us to write my similarity statement for these three. And what I mean by that is we'll just do an EG, which is here's an example for this particular situation. I want to start with the small left triangle. And I don't always have it small left because this thing could be oriented differently. And really, I don't care the order that we start in. But give me any of the three triangles that start with the letter L. Let's see. Carson, can you give me any of the three triangles up here that you can say starts with L? L-O. I'm okay with L-O-E. You're right, but I'm going to switch it because I do this specifically. But L-O-E would work. Could I instead use L-O-V if I wanted? That's a different triangle. Now, there's a reason that I tweaked what just happened, and we'll get it here in a second. I know that the way I've written this O is a what sort of angle for the big triangle that we're talking about. So I start at angle L, and then I go to a right angle in the middle. Do we all agree with that? Is there another triangle up on the board that starts with L and and has a right angle in the middle? So instead of going from L to O to V to get my right angle in the middle, I could go from L to where? To E to O. Notice, I have angle L's matching, so there's already an angle congruent, and I've arranged it such that there's a right angle in the middle. Both of these triangles are similar by what? Angle, angle. Before we kick on to the last one, have I lost anybody here? I always start with this and put the right angle in the middle. You do not have to, but this is the way that I keep it straight in my head. Now, the last triangle is always the hardest, but it doesn't have to be, but it's unnatural to look at this. Can we draw another triangle that starts with L? We can't do it. So here's where we have to be a little bit clever. When we're looking at this, all I know so far, I can't start at L, but what sort of angle must I have in the middle? So I need to draw another triangle that has a right angle in the middle, which limits me to two possibilities. What's one of them, Vincent? We've used the left triangle and the big one. Give me another way that you could talk about this other triangle with a right angle in the middle. VEO is one option. And if we go through that, we get VEO. And Tiadi, can you tell me, instead of going from V to E to O to make this triangle, as long as I want E in the middle, what's the other direction? Instead of going from V to E to O, if I want the same 3 points used, I start where instead? At O? So I see your lips moving, but I don't hear anything, and I'm sorry. I'm kind of deaf. Actually, I'm not kind of deaf at all. That's not true, but I don't hear very well because this thing is always roaring right next to me. You're good. Like, I don't even know. I can't tell if you're right or wrong. I'll come near you. That's okay. One more time. So I like that idea, and you're giving me different points, but if I go from L to V to E, I don't think I form the triangle. But instead of going here, can I just switch direction? So OEV would be the other alternative. Now, I spent a lot of time talking about those, and I fear we may have lost what we're really looking for. I need a right angle in the middle, and I can't start with L. Well, shucks. What does this triangle end with? V, and does it have a right angle in the middle? Yes. Is there another triangle on the board that has a right angle in the middle and ends with V?
Yes. Yeah.
What is it? If we go from O to E to V, I can't make the L's match up because they don't work, but I can make the right angle in the middle and V match up. These two are similar via angle, angle. These two are similar via angle, angle. And these two are similar via angle, angle. Everything is similar to everything else is what our theorem just told us, which is what we have written here. Now, our similarity statements are super duper duper important for us. The order matters big time. Big time. Because from these similarity statements, could we work out the scale factors if we wanted? Like, let's do that. We're going to do one of these. We have these statements. I'm going to keep the same triangle. We're just going to add some lengths to it. So we're going to do an example with this, and we're going to see what shakes out. So let's see here. Hypothetically, I'm going to just copy this triangle, but I'm going to erase this altitude and stuff. Not the actual altitude, just the word. I'm going to have the same triangle, same letters, so that we don't get goofed up just with the letter deal. I want to see something that's kind of neat the way it shakes out. If we have that exact same triangle, and do you want like concrete numbers, or do you want us to pick some just variables? Concrete or general example? Concrete, you got it. So let me find one with some nice concrete numbers. Oh, this one works nicely. So let's say we have on this lovely triangle, our goal is going to be to find OE. Our goal for this problem is I want us to think about how can we find the length of segment OE. Okay, here's all we know. We get this lovely thing with these right triangles added and one little tiny piece of information. I'm told that LE has a length of 15 and I'm told that EV has a length of 5. And I'm going to call OE X just for simplicity's sake and being able to write it so we don't confuse zeros. Our goal right now is to find X. Cool. Now, as I'm looking at these triangles, we've already decided they're all three what? Similar. Are there two triangles based on the similarity statement from above that both have the segment that we're after? And when I say the triangles above, I mean I'm looking at this similarity statement. Is there any of those three on which the segment which we're trying to find is on both of them? So OE, is it on the first one? Is OE on this red triangle? And is OE on the purple triangle? Well, that's my first little thought, like, hey, maybe I can use these two triangles in the fact that they're similar. As we start looking at this, let's just see what shakes out. If I want OE, and I'm just going to overline this, and I know that's a weird thing, OE shows up here. So if I wanted a scale factor, I can say X, because that's what we called it, to, what would that correspond with on the other similar triangle? EO, or X, matches with what part of this triangle? OE, be very, very careful. Our similarity statement is in a very particular order, like it has to be. This is the second and third. It must correspond with the second and third. What does it match up with? EV. And I know it's weird that we make that change, but we're just going, and that's our similarity statement and why we are like so crazy about it. Okay, what other length do I know on this triangle? LEO. I know LE, so if I commit to that, we'll just use it because it's what's given. LE, and I'll underline this, it corresponds to what on the other triangle that's similar to this? Anybody but Lily, because I can't tell if everyone's catching this or not. Would you, like, if you're struggling with this question, like, I'm not trying to, like, make it misleading, and this is just a weird arrangement thing. The similarity statement will wind up being the answer to these. What lines up with LE on our other triangle? OE. Now, I can get this from our similarity statement. If you guys would rather, like we did in this group, draw the picture out and arrange them, it's the same stuff. We're going to get the exact same answers. LE matches up via our similarity statement with OE. And what do we call OE on our picture? X. Now, this proportional relationship is going to take us to a very convenient definition. I'm going to do one more step before I start trying to solve it. Do we know what EV is? Do we know what LE is? 15. And now, here's my suggestion. I think we're at a point where we can solve it for x. I want you guys to solve this with your small groups for x. Solve this equation for x. Cool. I'm going to give you guys a second. There's some algebra skills that we haven't seen for quite a while. Talk it out with your neighbors.
You can multiply.
I'm going to be
Okay. X squared.
not going to be in your group necessarily, but I'm going to work closer here.
And then
You guys love fractions?
we just have to like
So,
square root it.
well, we didn't love fractions, but next year. Think
So-
back to Jarvis.
We can
That's
butterfly
all whoever you guys had.
like this. X
Always
times
something.
15 times 5 to get x squared equals 75.
I'm going to throw you one word, and you're immediately submitted. Like, I don't want you to just wait, but in the interest of time.
Yeah.
If I mention a cross,
And square root.
it's not the cross of Christianity necessarily, but the cross
But
just
you
in
know
general,
what
big
the
cross.
name that's called?
Louder.
What you do also.
You guys remember?
It's like, do you know what it's called?
Could be cross multiplication.
The cross multiplication.
Yeah.
Oh yeah.
You guys
Okay.
remember that one?
This singular problem, along with not forgetting that you have a quick short quiz on Monday to prep for, is your assignment over the weekend. Notice I didn't give you a ton more homework because I want you to go watch the game. I want you to have time to study. We will continue on here. Really quick short quiz on Monday. Not over this. Only 7.1, 2, and 3. Cool. Later, Raiders.